All right, welcome to the Explainer. Today we're unpacking one of the most intuitive yet powerful ideas in all of calculus, the mean value theorem. It's really the math behind a simple idea, that the story of your entire journey is always captured in one single perfect moment.
Okay, so let's kick things off with a question that feels, well, pretty obvious. Imagine you're on a long road trip. When you get to your destination, you figure out your average speed for the whole drive was exactly 60 miles per hour. So does that mean your speedometer had to hit 60 on the dot at some point, for at least a split second?
And the answer is a resounding yes. Now, you might be thinking, well, duh, that makes sense, but the reason it's guaranteed is a core principle that actually makes a huge chunk of calculus work. So that guarantee you get with the car trip, that's actually a perfect, real-world peek into the mean value theorem, or MVT for short. It's this cornerstone of calculus that takes our intuition and makes it mathematically rock solid. You can think of it like a bridge. It connects the average story, your speed over the whole trip, to the instantaneous story, what your speedometer says at one single moment. And the MVT is the thing that guarantees, it promises, that those two stories have to match up at least once. To really get our heads around the MVT, it helps to start with a slightly simpler, special case called Rolle's theorem. It kind of sets the stage with the same core logic, but in a much cleaner, more straightforward way. So, Rolle's theorem has a few rules of the game. First, the path has to be continuous, no breaks or jumps. Second, it's got to be differentiable, so no sharp, sudden corners. And the big one, the crucial rule for this specific theorem, you have to start and end at the exact same height. Think of it like this. If you go for a hike and you end up at the exact same elevation where you started, Rolle's theorem absolutely guarantees that somewhere on that trail, for just a split second, you had to be walking on perfectly flat ground. Your instantaneous slope, right then and there, was zero. All right, so that's Rolle's theorem. Now, let's bring on the main event, the full-blown mean value theorem. What happens if our hike doesn't start and end at the same elevation? What if we just kind of tilt the whole graph? Well, the MVT takes everything we just talked about with Rolle's theorem and just tosses out that one restriction. Your start and end points can be totally different. And now the theorem still guarantees a special point C, but instead of the slope being zero, it promises that your instantaneous slope will match your average slope for the whole trip. And this is what it looks like geometrically. That straight line connecting your start and end points, that's the secant line, and its slope is your average speed. The MVT guarantees that somewhere along that curve, there's a point C where the tangent line, your instantaneous speed, has the exact same slope. The two lines are perfectly parallel. That's the guarantee. Now, you might be looking at this and thinking, okay, that's a cool geometric trick, but it is so much more than that. The mean value theorem is the theoretical engine behind some of the most fundamental ideas in calculus. This thing is an absolute workhorse. And this is where the MVT really flexes its muscles. It's the proof that connects the derivative at one single point to the behavior of the whole function. Because of the MVT, we can say for sure that if a function's derivative is always positive, the function has to be increasing. If it's always negative, it has to be decreasing. It's a foundational rule, and it's the mean value theorem that gives us the mathematical backbone to make that claim. It also gives us this really deep insight into something called antiderivatives. Basically, functions that all share the exact same derivative. So how are they all related to each other? And guess what provides the proof? Yep, the MVT. It guarantees that if two functions have the exact same derivative, they have to be the exact same shape, just, shifted vertically. They're all part of the same family of curves, only differing by a constant. Okay, so we've established the MVT is super powerful, but how far can we take it? Let's push on this idea a little bit and see where it holds up, and where it, surprisingly, totally falls apart. This core idea, finding an average that has to match a specific moment, is so incredibly useful that it actually pops up elsewhere. It's not just for derivatives. It shows up in integral calculus too. Check this out. This is how it applies to integrals. The MVT for integrals guarantees that for any continuous curve, you can find a specific height, f of c, that represents the average height of the entire function. And if you draw a simple rectangle with that average height, you're guaranteed that its area is exactly the same as the entire complicated area under the curve. Pretty cool, right? Okay, but this all leads to a really fascinating question. We've seen this thing works for derivatives and integrals, But what happens when we leave our simple, one-dimensional road trip and start thinking about, say, the path of a drone flying around in three-dimensional space? And here's the big twist. It turns out the classic mean value theorem, this beautiful, intuitive guarantee that we've been talking about, it just stops working. That rock-solid guarantee we had for the car, it completely breaks down once we jump into more dimensions.
Okay, but why? Why does it break? Well, think about our drone again. Its average velocity is just a straight vector from its starting point to its ending point. Its instantaneous velocity is the vector showing which way it's pointing and how fast it's going at any given second. For the MVT to work here, there would need to be one single moment where the drone's instantaneous velocity vector points in the exact same direction as its overall average velocity vector. And for most squiggly paths in 3D space, there's just no single point in time where those two vectors line up perfectly. The math just doesn't guarantee it anymore.
So in the end, the mean value theorem is all about this incredible link between the big picture, the whole journey, and one specific telling moment. But its failure in higher dimensions is a great reminder that even the most fundamental ideas in math have their limits. It really makes you wonder, right? Where else in science, or maybe even in your own life, is that connection between the entire journey and one single moment the most critical thing to see?